graph of a function and its inverses are reflections across the line y equals x, which is just a diagonal line that goes through the origin with a slope of 1. So this line right here. Now, the reason that serves as the reflection line is because an inverse function is the result of flip-flopping the x and y coordinates of the original function. So if we take the example here, f of x equals 4x. If we graph that one, we can do it in blue. Hopefully we recognize that as being a linear function, so it's in y equals mx plus b format, where the slope is 4 and the y-intercept is 0. So if I graph that function, I'm going to go from the origin, from the y-intercept, I'm going to go up 4 over 1, up 4 to the right 1. I can go down 4 and back 1, and one more time. And so here's the graph. Whoops. Let's make sure that that actually goes through our points. Pretty good there. So there's the graph of our original function. Now to graph the inverse, we can actually do it without having to actually find the inverse function. We will in a moment, but we can just take all of the xy coordinates of this original graph and flip-flop them. So 0, 0 flip-flopped is still 0, 0, so our inverse function is going to go through the origin. Our original graph went through the point 1, 4, so our inverse function is going to go through the point 4, 1. This original graph went through the point 2, 8, so our inverse is going to go through 8, 2. And the same thing with the 2 points here in negative territory. That point right there was negative 1, negative 4, so we're going to flip-flop that and go negative 4, negative 1. And then for the last point that was here that we went through, it was at negative 2, negative 8. So flip-flopping that gives us negative 8, negative 2. And so we can draw a line that goes through those points there. So again, the blue line here is our original graph, f of x, and then the red line here is the graph of the inverse of f of x. And so if we tilt our head sideways and use this line here, this dotted line, this y equals x, and treat it as a reflection line, hopefully we can see that these two lines, the blue line and the red line, are indeed reflections across that line. For example, this point here, if I draw a straight line to the mirror line, this point here, those are the same distance apart. Here and here, these 2 points are the same distance apart. We can repeat that all the way throughout. So the red line and the blue line are reflections of each other across that line, y equals x. Now, we do want to find the equation of that function, and so we can go back to our technique of the inverse function. We can go back to that technique of flip-flopping x and y and solving for y. So remember, the original function is y equals 4x. So if I flip-flop x and y, I get x equals 4y. Now I need to solve for y, so I'm going to divide both sides by 4, and so we get y equals 1/4 x. And so that is the graph that we see here, where we've got a y-intercept of 0, and then we've got a slope of 1/4. We're going up 1 over 4, up 1 over 4, down 1 and back 4 for the graph of that inverse. For the next example, we're going to do the same sort of thing. We're going to graph the original function and then flip-flop the x and y coordinates and see that it is the resulting inverse function is indeed a reflection across that line y equals x. So for this one, it might be helpful for us to make a t-table of the inputs and outputs for our function, since it's not one that we're necessarily familiar with like the linear function before it. So if we plug in 0 for x, 0 plus 2 is 2, 2 cubed is 2 times 2 times 2, which is 8. So if I go over 0, I'm at 8 on the y-axis. Now if I plug in 1, I'm going to get 3 inside the parentheses, which cubed is going to give me 27. So I'm blowing up off the graph pretty quickly. So I'm going to try to go in the opposite direction and see what happens. So if I plug in -1 for x, -1 plus 2 is 1, 1 cubed is 1. So I'm going through the point -1, 1. If I plug in -2 for x, -2 plus 2 is 0, 0 cubed is 0. So this is working out for us, points that are on our graph. If we go to -3, -3 plus 2 is -1, -1 plus 2, or sorry, -1 cubed is -1. So we go -3, -1, and then finally if we plug in -4, this will give us one more data point. -4 plus 2 is -2. -2 cubed is negative times negative times negative. So it's going to be a -8. So -4, -8. And then after that we're going to be pretty far down if we keep on going. So our graph of our original function looks like this. So now again, we can generate the graph of our inverse function without even knowing what the equation of the inverse function is. We'll get to that in a minute, but we're just going to flip-flop the coordinates of the points that are on this original graph. So if we go to this top point right here, if you'll recall, that was at 0, 8. So my inverse is going to have a point at 8, 0. This point right here was at -1, 1. So I'm going to go over 1 and then down 1. So 1, -1 is going to be the corresponding reflected point. This point right here is at -2, 0. So we're going to have a point at 0, -2. The point here was at -3, -1. So I'm going to go -1, -3. And then the last point that we had on our original graph that we'll make use of was this one here, which was at -4, -8. So I'm going to go to -8, -4. And so now I've got this graph here that is the inverse of that original. And again, if you tilt your head sideways and imagine this as our mirror line, y equals x, hopefully we can see that those are indeed inverses. Those are reflections of each other across that line. So now for finding the actual inverse function, we're going to replace f of x here with y. So we've got y equals x plus 2 cubed. I'm going to flip-flop the x and y, so I get x equals y plus 2 cubed. And now I have to solve for y. So my first thing that I'm going to do is I'm going to get rid of that cube. So I'm going to take the cube root of both sides. So the cube root and the cube cancel each other out. So I get y plus 2 over here on the right. And then on the left we just have the cube root of x. And so then the last thing we've got to do is just subtract 2 from both sides. So we end up with y equals the cube root of x, and then outside of the cube root is a -2. And so we can go ahead and put that here. And so this is our inverse function. We want to make sure that we're using the inverse function notation. And so there's the equation that matches up with the inverse graph. So again, we didn't even need to know what the equation was in order to generate the inverse graph, because we could do it by just taking the original and flip-flopping all the x and y coordinates, and then just making sure that it looks like a reflection across the line y equals x.